All right, in this video, we're going to talk about simple harmonic motion. And simply put, simple harmonic motion is just a repetitive back and forth movement through an equilibrium or a central position. And for it to be simple harmonic motion, the maximum displacement on one side of the equilibrium has to be equal to the maximum displacement on the other side. So there are other forms of harmonic motion where the displacement on one side of the equilibrium is not equal to displacement on the other side of the equilibrium. One such example of that is damped harmonic motion, but we won't talk about that in this video. One example of simple harmonic motion that's easy to resonate with is that of a pendulum in a grandfather clock. So here I've drawn my pendulum on my grandfather clock. And we all know that a pendulum on a grandfather clock swings to the right and to the left. But that swing each time is equidistant from the straight down position. In other words, equilibrium is when the pendulum is hanging straight down. And then we have a maximum distance from that equilibrium to the right and a maximum distance from that to the left. And those two distances equal one another. So this is an example of simple harmonic motion because it's a repetitive movement back and forth through that equilibrium so that the maximum displacement on one side is equal to the maximum displacement on the other side. Circular motion can even is even an example of simple harmonic motion. Take, for instance, the Ferris wheel that I have here on the right. The equilibrium of the Ferris wheel would be as riders when we're sitting at the same height as the axis on the Ferris wheel. So when we're sitting here and here. But as we go around the Ferris wheel, we travel around, and then at some point, we're at the bottom, which would be our maximum displacement in the negative side. And as we keep riding, we make it to the top, and that would be our maximum displacement on the positive side. So even as we're riding a Ferris wheel, we still have a maximum and a minimum, or rather the displacement from an equilibrium. We're on the bottom, and then we're on the top, and then we're on the bottom again, and then we're on the top. And those bottoms and tops are equidistant from that central position, the equilibrium. So the first example is an example of simple harmonic motion where we have left-right movement. And then the second example is an example where we have up-down movement on the Ferris wheel. And there's some other applications of harmonic motion and simple harmonic motion too, when it comes to electrical currents and sound waves. And because simple harmonic motion is a repetitive motion over and over and over, it is cyclical. In other words, it is periodic. That means we can use our periodic functions to model simple harmonic motion. As we all know, our periodic functions are the trigonometric functions. And we can use sine or cosine to model simple harmonic motion. So here, we should all be familiar with this. This is just the basic organization of the sine function. But to model harmonic motion, we're going to rearrange it just a little bit, or we're going to actually change some of our variables just a little bit. We're going to have d. D just stands for the maximum displacement of the object. So how far the object has moved. And of course, the A is still good. The absolute value of A will still be the amplitude. Here, we've not seen this before. This is the variable omega. But when we were graphing sine and cosine functions, we had a variable here, and that variable was a b. But when we're talking about simple harmonic motion, we're just going to use the variable omega. So just know that omega and b are the same thing. And then we had c over here, and we know that c over b would always give us our phase shift or our horizontal shift. And then d here on the end represents a vertical shift, of course. So in these situations, our amplitude will be the maximum displacement of the object. The period will be the time that's required to complete one cycle. And the frequency will just be the number of cycles per unit of time. Now, this is something that's pretty new. Now, we're going to measure frequency in hertz. That's Hertz, and the abbreviation for that is Hz. And when we measure frequency in hertz, 1 hertz is equal to 1 cycle per second. And that's important to remember. It's 1 cycle per second. We also need to know that the frequency is just the reciprocal of the period. So if I were to graph one period of the sine function, we know that we would graph that over a period of 2 pi units long. Well, if the period is 2 pi, the frequency would be the reciprocal of that, 1 over 2 pi. So the frequency and the reciprocal are related. Now, how did we find the period of a sine or cosine function? We always use the formula that the period was 2 pi over whatever our b was. But in this case, we're not using the variable b, we're going to use the variable omega. So our period is equal to 2 pi over omega. But remember, the frequency is just the reciprocal of the period. So if the period's 2 pi over omega, that means the frequency is omega over 2 pi. And then the last thing that we need to take note of is our independent variable here is t. So essentially our equation here is going to model displacement for us over an amount of time. Displacement over an amount of time.